the spectrum of A is always closed, bounded, and non-empty. So this couldn't happen here, that couldn't happen because it's not closed. This could happen. Okay, so let's attempt a proof of this beautiful little lemma. Okay, claim 1. Why is the spectrum closed? To see that the spectrum is a closed set, one has to show that its complement, which is the set of all complex numbers that are not in the spectrum, is an open set. Okay, so what's the complement? Lambda is in the complement if and only if it's not in the spectrum, so A minus lambda I is invertible. So this is the statement for the green points here, maybe this lambda. But then we had this lemma in section 3.1, which said that invertibility is infectious, that's what we called it. And here it means that you can wiggle a little bit around that point lambda, and still the new operator A minus lambda I is invertible. So it means there's a little neighborhood of every green point that is still entirely green. But that's exactly what it means for the complement to be an open set. But if the green set is open, then its complement, which is the blue set, is closed, which proves our first claim. Okay, second, boundedness. Let me draw a new little diagram of the spectrum in the complex plane here. And remember what boundedness of a set means. It means you can cover the set by a disk no matter where the midpoint of that disk. So you can just enclose it in a circle, and it doesn't matter where you put the midpoint. You could take that circle, or you could try that circle here. So boundedness means it fits inside a circle with a finite radius, and the most natural choice for the midpoint is usually the origin of the complex plane. Okay, maybe it's here. It could be in the spectrum, it could be outside, it doesn't matter. What matters is that you find a radius that is finite, but large enough so that this circle here encloses the spectrum, or so that this whole disk here covers the spectrum. Good. How do we prove that? Well, the best thing is to just write down the size of that radius. Well, let's start with something that we know, and that is eigenvalues. We know from our linear algebra course first year that the eigenvalues form a bounded set, and that you can cover them by a disk around the origin, and the radius of that disk is norm of A. How do you see that? Well, you start with this equation, ax equals lambda x, then you put norms. Then you recall that the norm of lambda x is just modulus lambda times norm of x, whereas on the other side you have an inequality by operator norm of A times norm of x, and then you just divide by the norm of x, which gives you your claim. Okay, but that was just for eigenvalues. Now let's see whether we can bound the rest of the spectrum also by norm of A. Let's try. And let's assume that the converse is true. Then let's rewrite our operator A minus lambda I a little bit, and let's aim for something that looks like identity minus a little operator. So we have to get that minus lambda out of the way. So we are left with the identity from here, and now minus 1 over lambda times this A. But indeed here we get our little operator, because its norm can be written as 1 over modulus lambda times norm A, but that's less than 1 by our assumption. So indeed here we have identity minus a small operator, one which has norm less than 1, which makes this operator in brackets here invertible by Neumann series, which we also discussed in section 3.1. Okay, and then this factor in front here is of course non-zero because lambda is larger, or modulus lambda is larger than some non-negative number. But that makes the product, which is this operator, invertible, which of course contradicts the fact that lambda is in the spectrum. Okay, so indeed this claim here must be true, and that's how we see that the spectrum is bounded. By the way, at this point we have already learned something more about one of our examples up here, which was example A. In example A, we looked at the backward shift, and we only focused on eigenvalues. And what we showed is that, well, depending on which P you take, the set of eigenvalues is either the closed unit disk or the open unit disk. But we didn't discuss the spectrum. Now, in both cases, we can say what the spectrum is, because we know that the spectrum is always a superset of the set of eigenvalues. So it must be at least the closed unit disk or the open unit disk here. On the other side, it is closed by our lemma, 0.1. And it is bounded, and it's in fact bounded by a circle around the origin that has radius norm of A. And for the backward shift, it's a very simple computation to show that the norm of A equals 1. Ask me in the exercise session if you don't see it by yourself. But then it's clear that the spectrum is contained inside the closed unit disk. So it's contained in the closed disk around the origin with radius 1, which is this red set. So the spectrum is between this closed unit disk and the closed unit disk, so it must be the closed unit disk. And here in the p equals 1 case, the spectrum is between the open unit disk and the closed unit disk, but we also know it's closed by, lemma 1.1. So it also must be the closed unit disk here. Okay, that was just a comment looking back to example A with already the 2 points that we have now. Well, it remains to prove claim number 3, the spectrum is always non-empty. For this part of the proof, look at the function f that takes a complex number lambda and turns it into the operator a minus lambda I inverse. In order for this inverse to exist, you should of course avoid points in the spectrum. And now assume the contrary of our claim holds, which makes our function f a function on the whole of the complex plane. And then one can show that f is a holomorphic or analytic function on the complex plane with values in the operator set L of x. If you took a course on complex analysis or complex function theory, then you will have heard about this concept, but probably with complex values instead of operator values, but it doesn't change very much really. Okay, the next property that we get is boundedness. Well, first of all, f is bounded on every compact set because it's a continuous function. And so it is bounded on the closed disk around the origin with radius norm of A. So this notation refers to the closure of the ball of radius norm A around 0. But f is also bounded on the exterior of that circle. And to see this, we need a little computation. And for that computation, we start with the same, well, should we call it trick? Same trick that we used in the previous statement number 2. So we write a minus lambda I like this, which gives you minus 1 over lambda in front, and then the inverse of that operator in brackets, which you of course compute by the Neumann series, because just like in the previous statement, we have that now modulus of lambda is bigger than norm of A because we are outside of this ball. Disk, we should say. So we are just spelling out a bit more explicitly what we said anyway in part 2 of the proof. Okay, now how do we see this expression is bounded? Well, we have to compute its norm. It's an operator, right? So let's start by copying this expression here. Then get the modulus of this factor out. Then apply triangle inequality here. And submultiplicativity here. And then of course you can get the modulus of this factor here out again. And here you apply just the geometric series formula and simplify. So why is this bounded now? We're still claiming this. Okay, let me make a little trick. Let me get a factor 2 in front here and here, which doesn't change any of the arguments. So if modulus lambda is bigger than 2 times norm A, then it's still bigger than norm A, so we can keep all of this. But now we can use that modulus lambda is bigger than 2 norm A. And consequently, the whole fraction is less than 1 over 2 norm A minus norm A, which is of course just 1 over norm A. So indeed, f is bounded outside this disk and is bounded on the disk, so f is bounded as a function on the complex plane. But then comes Liouville's theorem, which you've probably seen if you took a course on complex analysis, which also exists in a version for vector or operator valued functions on the complex plane. And it says if f is holomorphic on the whole of the complex plane and is bounded, then it must be constant. But that, of course, doesn't sound right, because how do we argue best? I mean, we could pick 2 different points and show it's different there. Or we could reuse this argument here to show that modulus norm of f of lambda goes to 0 when modulus lambda goes to infinity. And the constant function that converges to 0 must be the 0 function. But of course it's not, because it's the inverse of some operator, so it can't be the 0 operator, which is not the inverse because it's not invertible. Okay, and this shows that our assumption of the contrary is again wrong, so that the original claim is true, which finishes our proof of number 3 and hence the proof of the whole lemma. So this lemma 1 shows that if M is a set in the complex plane, that is the spectrum of a bounded linear operator on a Banach space, then M is closed, bounded, and non-empty. And as so often, we ask ourselves whether maybe even the reverse implication holds. And interestingly enough, the answer is yes. So if you're given a subset of the complex plane that is closed, bounded, and non-empty, maybe like this, and a little bit over here, then you can construct an operator, a bounded linear operator on a Banach space, whose spectrum that here is. And to find such an operator, you start with a dense countable subset of your set M. What means dense? Dense means a set whose closure is all of M. And countable means you can enumerate the points like 1, 2, 3, 4, 5 and so on up to infinity usually, because in general your set M will be infinite. And you could, for example, take points with rational coordinates in M, and that already makes it countable. And then you take an operator A on a sequence space and let A act by multiplication by the infinite matrix that has A1, A2, and so on its diagonal. You will immediately see that they become eigenvalues and hence spectral values of A. So it's clear that the subset S is part of the spectrum, but we know that the spectrum is always closed, so the spectrum is at least the closure of S, which is M. But we can show it's not more than that. So indeed, you have found an operator whose spectrum is your rather exotic set M that you started with. And it's a bounded operator because this is a bounded sequence, because this was a bounded set.